Hello dear attendees, I'm Shada, Melise Terkaraman. Today I'll talk about the study on an improved hybrid genetic algorithm for the quadratic assignment problem that I carried out with my instructor, Dindar Oz. Before I begin, I would like to thank you all for your understanding about my way of presenting, arising from my speech disorder. As one of the most studied combinatorial optimization problems, the quadratic assignment problem, or shortly QAP, has various applications in real life, including the planning of a campus, the design of a hospital, the placement of electronic components, and many more. That's why it's a problem attracting academic researchers and scientists for many decades. We will talk in the definition part in details, that the QAP has a quadratic objective function, and it falls within the NP-hard class. Since exact algorithms are impractical for the large instances of the QAP, many heuristic methods have been proposed to provide near-optimal approximate solutions in a reasonable computational time. Moreover, several classic NP-hard problems, such as the traveling salesman problem, the maximum clique problem, the bin packing problem, and the graph partitioning problem, can also be recast as a quadratic assignment problem. Now, let's define the QAP in both formal and informal manner. In QAP, we try to have a one-to-one assignment between the facilities and the locations with the minimum cost. A one-to-one assignment means that each facility will be assigned to exactly one location, and each location has exactly one facility allocated to it. We said minimum cost, so we have to provide a cost function. There is a distance between each pair of locations, and there is a weight, or flow, is specified for each pair of facilities. The cost is calculated as the sum of the distances multiplied by the corresponding flows. Formally, we have two sets. Set F contains n facilities, and Set L contains n locations that can host the facilities. F sub ij represents the flow from facility I to facility j for all I and j in the set F. D sub uv represents the distance between locations u and v for all u and v in the set L. QAP involves determining assignment of n facilities to n locations with a minimal cost. Clearly, a facility location assignment can be represented by a permutation pi, such that pi of I represents the assigned location of facility I. Let the omega denote the set of all n permutations, then the NP-hard QAP can be formulated as the sum of the flows multiplied by the corresponding distances. To solve the quadratic assignment problem, we propose an improved hybrid genetic algorithm, shortly IHGA. It's improved because we employ a randomized greedy heuristic for the initial solution generation and diversification stages of the classical genetic algorithm. It's hybrid because we combine the improved genetic algorithm with a simulated annealing algorithm. Before we dive into the details of proposed algorithm, let me show you how a solution of the QAP is represented. As I said in the formulation, the permutation is very convenient to represent the solutions of QAP. Here, the permutations are nothing but a non-repeating sequence of integers, from 0 to n-1, where n is the number of facilities and locations. In the figure, you can see a sample solution with n equals to 6. The idea is that, if the number I is at index u in the permutation, then the facility I is assigned to location u. In the sample permutation, the facility 4 is assigned to the location 0, the facility 1 is assigned to the location 1, and so on. Via this representation, the constraint of one-to-one assignment is automatically handled. This is the schema of the proposed algorithm. The algorithm mainly consists of three components. We generate initial population of the GA, with a greedy algorithm. We also use the solutions generated by the greedy algorithm, within the GA. Then the best K individuals are being improved by a simulated annealing algorithm. Let's take a look at these components one by one. For the greedy algorithm, intuitively, a location facility pair is a good component description. In our approach, the first location facility pair is selected randomly. In the rest of process, the unassigned location with the largest sum of distances is paired with the unassigned facility with the smallest sum of flows, in order to keep their multiplication as small as possible. The individuals we generated through the greedy algorithm constitute the initial population of the improved GA. So we ensure that the GA part of our algorithm starts with relatively good individuals. To prevent the premature convergence, we apply the population partial reinitialization, depending on the repetition of the best individual, over a number of iterations. The individuals to be replaced with a part of the population are also generated via the greedy algorithm. In this way, we boost the divergence of the population, with some fit individuals, rather than some randomly generated individuals. Once the improved GA part of our algorithm terminates, a few distinct promising individuals in the final population are improved through a simulated annealing algorithm, which is a single solution-based metaheuristic method that originates from an analogy taken from thermodynamics. In the essay, the cooling schedule determines the initial temperature and the temperature's updating policy. We used a logarithmic update function in the improved hybrid GA. In the experiment phase, we used 50 QAP instances, with the size between 12 and 90, both inclusive. Only 9 of them are taken from the QAPlib, which is a quadratic assignment problem library containing various problem instances and optimum results. We implemented a random problem instance generator, and created 41 more instances similar to Teilhard's instances. We used 1/5 of the instances to tune the SA and the GA parameters of the improved hybrid GA. In the parameter tuning phase of the SA, we have seen that the average objective value has been the minimum for 9 of the 10 problem instances, when the initial temperature is 2000. When we come to the improved GA, after a trial and error process, we have decided to reduce the number of parameters by defining some of those in terms of the others. For example, we define the mating pool size, the number of offspring to include in the population, and partial reinitialization size, as some fractions of the population size. In the light of obtained results, we have selected the parameter values, as orange-colored part, in the slide. we designed an experiment to compare the performance of our improved hybrid genetic algorithm with that of the greedy algorithm, simulated annealing algorithm, demon algorithm, and a classical genetic algorithm. You can refer to our article for the experiment configurations. The result table is too large to present here. So these are the results of the problem instances taken from the benchmark. After we obtained the average objective values by each algorithm, we calculated success percentages based on the optimum values in the QAP lib. The algorithm we proposed achieved the highest overall success percentage with 98.67%. The SA followed our algorithm with 98.51, due to its high iteration count in each run. Here, the objective value averages of the improved hybrid GA are subtracted from those of other 4 algorithms, and these differences are plotted as in the chart. As the problem size increases, the gaps between the achieved objective values are increased. We have talked about the success percentages based on the benchmark instances. Here, we share the improvements based on all the instances. The improved hybrid GA produced up to 1.06 to 21.28% better solutions than the other algorithms. Finally, to ease the comparison of the 5 mentioned algorithms, we utilized a ranking method based on the Formula 1 scoring system. Our algorithm comes first with the total score of 392 over the maximum possible score of 400, among the 4 algorithms having 336 to 160 points. To sum up, we propose an improved hybrid genetic algorithm, which mainly combines a greedy heuristic and a simulated annealing algorithm with the classical genetic algorithm. We test our algorithm on a well-known benchmark for the quadratic assignment problem, and compare the results with 4 different algorithms: a greedy algorithm, simulated annealing algorithm, demon algorithm, and a classical genetic algorithm. The results of the experiments validate that our hybridization significantly improves the performance of the algorithms, comparing to their standalone executions. Before I end my talk, I can say that a more comprehensive parameter tuning process can enhance the results of our algorithm further. Moreover, dynamic diversity boost through the iterations of the GA and parallelization of the SA part of the proposed algorithm will be nice future works. Thank you all for your attention. All the questions are welcomed, if you have any. My instructor Mr. Oz, or I will be answering them.